Today, you and I are going to understand what curved spacetime actually is, and take some first steps towards understanding how it can explain planetary orbits and the fact that objects fall down. Not because gravity is a force, but because gravity is something a lot deeper than that. Planets or astronauts follow geodesics in a spacetime manifold that is curved, due to the presence of massive objects like the Sun. In order to get to all of these beautiful things, like planetary orbits or the bending of light, we'll first talk about how massive objects distort the fabric of spacetime. In order to see what happens to spacetime due to the presence of massive objects, we start with flat spacetime, so no masses for now. We equip flat spacetime with a coordinate system, where one unit of coordinate axis corresponds to 1 kilometer. What we see here is quite trivial. The distance between 2 points within our manifold can easily be calculated using the coordinates. So the distance between two observers located at r equals 5 kilometers and r equals 11 kilometers is, well, simply 6 kilometers. And similarly for distances anywhere else in our manifold. And now we'll add a mass into our system. The mass that I'm choosing here is about 67% the mass of the Sun. However, condensed to a radius of just a few kilometers. And now something interesting happened. Imagine we kept two observers at the same coordinates as before, at r equals 5 and r equals 11. If they measured the distance between them once again, they would measure a distance that is longer than what they measured before. They didn't move or anything, but the physical distance between them increased. Something quite bizarre happened. Space itself changed due to the presence of mass in our system. If they do this measurement at different locations, they find that space gets stretched more and more the closer you are to the center of the coordinate system, which you can see by comparing the coordinates on the axis and the distance they measured. Also, everything is spherically symmetric, so doing the same measurement here along the y-axis, or any other axis that goes outwards radially, yields the same result. As you do the measurement infinitely far away from the mass at the center, you would see that space gets stretched less, and the distance that you measure now is essentially the same as before, in the case without a mass. So you could say that the coordinates that we're still using to describe our manifold are the coordinates of an observer who is infinitely far away. Next, I'll show you a way to understand this stretching of space in a more geometrical way, one that can, however, be a bit misleading. We'll go to a three-dimensional representation of the two-dimensional plane that we've been looking at. Now, this picture might be familiar to you, and now we'll understand what it actually means. As we just discussed, the physical distances that you measure after inserting a mass into the center of your coordinate system change compared to a measurement without a mass. Without any mass, the distance between two observers that are positioned at r equals 5 and r equals 11 is simply 6 kilometers. Now, with the mass, the distance between the two observers that quite crucially do not move increases to about 7 kilometers. Now, the distance that you see here is precisely the distance when you follow a direct path on the curved manifold, which is now longer due to the curvature of the surface. With this visualization, you can quite intuitively understand where space got stretched more and where it got stretched less. As we go towards the mass, the curvature becomes stronger. And as we go away from the mass, the curvature becomes weaker. But quite crucially, this geometrical representation of the curvature merely shows how distances get stretched due to the presence of a mass. Now, I would like to clear up some potential points of confusion that may have come up. With everything that we discussed so far, i.e. that masses stretched the space around them, what happens if you put another massive object, like an astronaut, somewhere on this manifold? Does it start moving? Perhaps fall towards the Sun? Well, the answer is shown on screen. Nothing happens to it. It just stays where it is. I mean, sure, in reality it would fall towards the mass. But the reason for that is not the curvature that you see on screen, at least not on its own. Instead, the reason is that time also gets deformed due to the presence of a massive object. But we haven't even talked about that yet. I think this misconception comes from the fact that this animation suggests a clear sense of up and down. And well, things tend to fall down, don't they? Well, firstly, this relies on the intuition that gravity is a force that pulls things down. However, in general relativity, gravity is not a force, Instead, objects follow geodesics through curved spacetime, as we'll explore in more detail in upcoming videos. Secondly, what you see in the animation is a three-dimensional representation of a two-dimensional plane. So we're still just looking at the xy plane around the massive object, and we're using the third dimension to visualize the curvature of it. So, what is the actual reason that the astronaut falls towards the central mass? In order to answer that, we need to talk about time. We'll first go back to flat space, without any masses, to see what's going on here. For now, everything is rather straightforward. Clocks of different observers run the same no matter where they are located. Unless, of course, one of the observers is moving with respect to the others. But if all observers are stationary with respect to the coordinate system, their watches run the same. Now, let's again add the sun to the scene. If we compare the clock rates of different observers now, we see that the clocks do not run the same anymore. Moving one observer closer and closer to the massive object, her watch ticks slower and slower. As an observer moves towards infinity, his watch runs faster, but the rate converges against some value. So, not just space gets stretched, but the entire fabric of space-time gets deformed due to the presence of massive objects. Now, for this last part, we'll see how to describe this mathematically. First, we saw that distances get stretched, and the amount depends on the position. Therefore, we have to work infinitesimally and say that dl, the actual physical distance, equals some function that depends on r, and probably also the mass m at the center, times an infinitesimal coordinate distance dr. As we discussed, r can be thought of as the distance from the origin in the absence of any massive object, and we still use it to describe the manifold, even after the mass gets added. Alternatively, you can also think of it as the coordinate of an observer positioned infinitely far away. For time, we do something similar. We saw that for stationary observers, time runs slower and slower the closer you are to the mass. So d tau, the actual time that passes on a watch of the observer, is also some function of r and m. Here, we will relate everything to an observer at infinity. So d tau is equal to some function times dt, where dt is a time interval measured by the watch of an observer at infinity. These two functions are given by the following. If you examine them in more detail, you see that, indeed, the closer you are to the mass, the more distances get stretched, and time runs more slowly the closer you are to the mass. To address one question that you surely have, why does mass curve spacetime like that? Well, actually no one really knows the answer to that on a fundamental level. Regardless, we know how to calculate the curvature of spacetime for a given distribution of mass due to this guy and his equations, which he published in 1915. But I'll leave the glory details of that for another video. But we can still make some further steps towards understanding it. In a previous video, we talked about the necessity of something called the invariant interval in the framework of special relativity, which holds true in flat spacetime or in the absence of any massive objects. We saw the following formula and also learned how to interpret it. It is a notion of distance between any two events that happen somewhere in the manifold. If it is negative, its absolute value can be interpreted as the time that passes on the watch of an observer traveling between the two events, times c to convert it into a length. If it is positive, it describes the distance between the two events in a frame of reference where both events happen at the same time. As we only talked about systems with spherical symmetry, it is better to use polar coordinates. Let's first look at the time measurement, where the observer doesn't move. In that case, the spatial part is 0, and everything simplifies to this. As we add a mass into the system, this equation isn't quite accurate anymore. Instead, we saw that the relation between the time that passes for an observer at r and an observer at infinity, where spacetime is flat, is the following. So let's include that into our invariant interval. In the second case, we measured the distance between 2 points on a radial line of the manifold. As it's radial, we can set the distances of the two Euler angles to 0. Also, a distance measurement is defined to be at equal time, so the time part also drops out, which reduces the equation to the following. This is true in flat spacetime. However, with the mass in the system, we saw earlier that the coordinate distance is related to the actual physical distance in the following way. If we also include that into our equation, we arrive at the Schwarzschild metric, which can also be rewritten as such, where g mu nu is called the metric tensor, a generalization of the Minkowski metric. This equation tells us how spacetime is curved in vacuum around any distribution of matter that is spherically symmetric. In this video, I gave more of a phenomenological explanation of the Schwarzschild metric, but historically it was the first analytical solution to the Einstein equations. In the next videos, I want to talk about how the curvature of spacetime affects the motion of objects, so we will revisit geodesics, this time in curved spacetime.